the web work homework section, and because they put too many composed functions on the homework, which again, I apologize for that. I didn't realize there were that many in there. Stop doing the homework out of web work. You can also take it out of the textbook, all right? Because if you look at the problems in the textbook, none of these have arguments on the inside other than x, all right? Which is what you should have been doing in 4.10. So let's take a look at some of these. Anything like this could show up on the test. I gave very basic ones. There are 11 problems on the exam. And I also gave a very specific review. So the review tells you exactly which problems out of web work are similar to ones that are on the exam. If it is on the exam, it's on the review. Because I literally went through and crossed them out as I put them on there. So they're on there. Yes? Question?
No, just
okay. All right. We're doing that? Yeah. Took a little longer, but I got it. Okay. So let's look at this one. So this is out of 410. These are antiderivatives. So if I'm looking at this, first thing I would do is I would fix the 1 over x squared and rewrite it as x to the negative 2 because it's easier to do the power rule. Just like when you do the derivative, it's easier if it's written in power form. So I would write x to the negative 2 plus x dx. Now, these are added together, so what can you do when they're added? You take the integral individually. Now, eventually, you're going to get to the point where you are going to not split them up. But for right now, probably you want to go ahead and split them up. Eventually, you'll just go from here to the answer. Even from here to the answer, without anything in between. But at this point, you're just learning it, so you can take more steps to make sure you get a solid foundation. Power rule in reverse. And in reverse means in reverse order too. So power rule brings the power to the front, then subtracts 1. So the first thing you have to do is add 1 back, and then divide by what the new power is, because that undoes the multiplication. So it goes in reverse order. You do the reverse thing in the reverse order. Okay? So then the next thing you're going to do is this one. What's the power on x?
1.
So you're going to add 1. And then you divide by the 1 plus 1, because that undoes having multiplied by it, bringing it to the front. And then what do you always add at the back?
Plus C.
And how many points do you lose if you forget it? 3. You will not do it very often. Okay, so this would give me, depending on how you want to write it, negative 1/3 x to the negative 1.
How's it?
Huh?
Where did you get the word? Yeah, where's the word?
I don't know. It should be negative 1 x to the negative 1 plus x squared over 2, 1/2 x squared plus c. You could also write it like this. That's also okay.
Which one would you prefer?
I don't have a preference. Yeah, doesn't matter to me. It depends on what you're doing with it, which form you might leave it in. Let's look at another one. So this is 471. You have the integral of e to the x minus 3x squared plus sine x dx. Okay. So if you're looking at these, you would split them up. Integral of e to the x dx. Now remember that a constant does not affect the integral, just like the constant doesn't affect the derivative. So you can pull the constant outside of the integral. The derivative we typically don't, but with an integral we usually do. All right, it makes the integral easier to compute. So I would pull the -3 outside the integral, but the x squared dx has to stay behind. The integral symbol is sort of like a force field. Anything that has the same variable as the differential cannot cross the integral, right? Like a limit. If the limit depends on x, then x cannot be brought out of the limit, but other things could be. The integral is the same thing. Because the differential is dx, anything with x in it cannot pass out of the integral. It has to be integrated to come out. And then the last one would be plus the integral of sine of x dx. And then you undo the derivative. Well, the derivative of e to the x is e to the x, so that's done. For x squared, you do the power rule, reverse. So the -3 is just tagging along at the front. Add 1 to the power, divide by the new power. That's going to give you x cubed over 3, but the 3 will cancel the -3, right? So you should end up with e to the x minus x cubed. And then what is the antiderivative of sine?
Cosine.
Yeah, you got to be careful here. And it gets to the point, right now you know the derivative of sine is cosine, the derivative of cosine is negative sine. But in Cal 2, at some point, you're going to make a switch in your brain. And you're not going to think so much in derivatives, you're going to think more often in terms of integrals, all right? So when you see the integral of sine x, you know it came from cosine, so there's got to be a negative involved, all right? So this is going to actually end up giving you a negative cosine of x.
And then the differentials.
And don't forget your plus.
The differentials just get dropped, I guess, right?
It's not dropped, it is telling you what to do the antiderivative with respect to. It's the notation,
Okay.
right? This is a bookend notation. You need both parts. Just like when we do the derivative notation, this is the derivative with respect to x. This is the integral with respect to x. It's all one notation.
That makes it.
Split apart. Tanner?
So for the exam, do you want us to show it, breaking it up in steps, or are we okay to just,
If you can go straight to the answer, that's fine with me.
Okay.
Just keep in mind on a test, the less you show,
The more likely you.
the more likely you might make a careless mistake, but more to the point, the fewer partial credit points you get if you make a mistake. If it's correct, it's fine. My rule of thumb is if I can do it in my head, probably a lot of you can too. If I can't do it in my head,
Yeah.
maybe one student or two,
Depends on the,
but it makes me a little
what your
suspicious.
math major.
All right, let's look at another one.
Could you do number 14 from that book? Because that was a reading one.
Yep, if you tell me what it was. I don't have it. So let's, while you're putting that one up, let's look at this one. This is 487. So it is the integral of 4 cosecant x cotangent x minus secant x tangent x. Now, if you're going to have an integrand with more than one term in it, you should have parentheses around the integrand, right? If you've got more than one term inside the integral, you should have parentheses around the entire integrand. Otherwise, it only applies to the first one. So
This is a difference rule, right?
So this one is just the difference of the two, but I would probably just go ahead and split them up. The constant comes outside, cosecant x cotangent x minus, I treat the negative like a constant, just pull it outside the integral, and then you have secant x tangent x. Don't forget the differential on either one. All right? Now you have to ask yourself, what function has a derivative that is cosecant cotangent?
Cosecant?
It is cosecant, but the derivative of all cofunctions is
Negative.
negative. So I'm going to need a negative when I undo it. So this would give me a -4 cosecant of x. Yes, because the derivative of this,
Wouldn't it be squared?
no.
No.
What is the derivative of -4 cosecant x?
4 cosecant tangent.
4 cosecant cotangent. Because the derivative of cosecant is negative, that would give me a double negative, which would make it positive, and I'd have cosecant cotangent. That's not squared. The one that's squared is the derivative of cotangent. That gives you negative cosecant squared, and derivative of tangent is secant squared, right?
That's right.
So over here, what function do you know has a derivative of secant tangent? Secant. So you get a minus secant of x and plus c. That's it.
That is so much easier. Stuff over 7.
Okay? So you're literally just undoing it. Ecom, did you find the one you were looking for?
Yes.
What is it?
No.
I will look at it. Oh, this is the stone. 25 feet per ground, 14 feet per second. So he's standing on a cliff? Or a roof? I don't care. Okay, no roof is 825 feet above the ground. It's a cliff.
No safe one.
Unless it's a high-rise building. Okay, and the stone is thrown straight up. 14 feet per second. All right, so you're standing here, and the idea is that it's not thrown because it needs to come from the edge of the cliff or the building or whatever. So you have a stomp rocket, right? So you stomp on it, it's sitting on the ground, and that shoots it up in the air. Okay? So the stone goes straight up at 14 feet per second. 14 feet per second sounds like velocity. So this is going to be velocity. And what are the questions that they ask us?
How high is the stone 2 seconds later?
How high is the stone 2 seconds later? Blah, 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 blah. Okay. What is affecting the stone once you stomp on the stomp rocket and the stone leaves? Gravity is the only thing affecting it. That's it. Well, technically air. Yeah. We have a little, yeah, you're right. What is the force of acceleration due to gravity in feet? That's feet, so it's gotta be feet.
32.
32 feet per second.
Yeah.
Negative 32 feet per second squared. That means every second of fall, you fall 32 feet faster than the previous second. So the first second you fall 32 feet, the second you fall 64 feet, the third second you fall 96 feet until you reach terminal velocity because of air resistance. Otherwise you would continue to fall faster at 32 feet per second of fall. Okay, so if that is my A of t, I need to come up with the position because they want to know where it is after 2 seconds. So what is the relationship between position and acceleration?
Second.
It's the second derivative. So acceleration is the second derivative of position with respect to time. So to get to position, I need to undo the derivative. That sounds like an integral. All right, so I'm going to integrate with respect to what variable? T, because that's what the functions are with respect to. So when I integrate the second derivative, I end up with
First derivative.
the first derivative. All right, up to a constant. And I'm going to put the constant on the left side Because if I had a constant on the right and a constant on the left, could I put the two constants together? You can. We roll them all together into one. So this would give me a C1, and this is going to give me, well, what, if I integrate acceleration, what would you get now?
Velocity.
It's velocity. But I know something about the velocity, but I'm going to take the negative 32 feet per second squared and integrate it. Do you see a t in this function here?
The second squared.
But there's really no t variable in here, is there?
It's just a
TX.
graph.
So it's just a constant. So can I pull the whole constant out of the integral?
Yes.
Yes, you can.
It'd be negative 32 over.
It's negative 32 feet per second squared. The integral of dt. What is the integral of dt? T, because the antiderivative of 1 is t. So this would give me negative 32 feet per second squared times t plus some c2 equal to s prime of t plus c1. In differential equations and calculus, when we have two constants like this running around, we just roll them all together into one
So we just say 2c.
plus c.
Are you recording?
I am.
Okay.
All right. So once I get to here, before I go any further, I actually know something about this function. This is velocity, right?
It's 14.
Which is
14 feet per second.
the first derivative. Oh, well, I've got that on the other side. What did I know about velocity?
14 feet per second.
It's 14 feet per second when?
Times 0.
At t equals 0, right before I stop it, or right as I stop it, right? That's the initial velocity. It's not moving at 14 feet per second all the time because it leaves the stomp rocket at 14 feet per second, but as soon as it starts moving, it starts slowing down. Why?
Gravity.
Gravity, right? And it's eventually going to reach a maximum height, at which point it will stop. So velocity is 0, and then what will it do? It will begin to fall, so it will be accelerating and the velocity will be increasing. Okay? All right, so I should be able to figure out what my constant is by plugging 0 in for t. So v of 0 should be 14 feet per second. And notice my units do work. Feet per second squared times time. This should be a second. Cancel one of those. I should get per second. That fits. All right. So when I plug this in over here to my formula, I should have v of 0 is 14 feet per second. And it's negative 32 feet per second squared times 0 plus c. Well, what's anything times 0? 0. Other than infinity, which isn't a number anyway. So this all goes to 0, so what's my constant? 14 feet per second. So now I have v of t is negative 32 feet per second squared t plus 14 feet per second. What am I trying to find again?
Position.
Position, right? I want to know where the rock is after 2 seconds. Is that right, Ecom? Okay. So after 2 seconds. So I need to integrate again because velocity is the first derivative. So to get s, and again, this would roll up another constant, but I'll just roll it into the right side. So I'm going to integrate this one, negative 32 feet per second squared, t, plus 14 feet per second with respect to time. And what does that give us?
T squared over 2
16 feet.
So the power on t is 1. So I raise it and make it a 2, but then I have to divide by the 2.
Negative 16.
So I have negative 32 feet per second squared times
T squared.
t squared over the 2, right?
Yeah.
And then I've got, well, this is just a constant, so the antiderivative is t, 14 feet per second t plus c. Okay? Now, at this point, we have to decide where we're going to fix our origin, which typically you would fix it down here, right? That's 0 height. So, Audrey, do you have a question?
Yeah, is that 2 from the, like?
The 2 is,
Did they give that to us, or?
no, the 2 is from integrating t. You add 1 to the power and divide by it.
Okay.
So it's the divided by it. So this gives me negative 16 feet per second squared, t squared. Notice the units will work. Time will be second squared, which will cancel second squared. It'll give me feet. That's what position should be. And then this one, feet per second times seconds should give me feet. So the units work, so you can feel pretty confident it's correct. Where did it start when t was 0? What was your initial position?
825.
It was at 825. So right here, S of 0 was 825 feet. And V of 0 was 14 feet per second. So I can plug in 0 and I get negative 16 feet per second squared times 0 squared plus 14 feet per second times 0 plus C. And that should give me 825 feet. So finally, up here, my position function is negative 16 feet per second squared t squared plus 14 feet per second t plus 825 feet. Which, if you've done physics before, do you recognize this?
It is kinematic equation.
This is your
Standard position.
V naught
Yeah.
and S naught, right? Your initial velocity and your initial position. And that's the standard formula for an object moving under the influence of gravity. Okay? So now if they ask us, where is it at 2 seconds, what would you do?
Plug 2 for T.
2 for t. So S of 2 seconds would give you 2 seconds squared is 4, so that's negative 64 feet, because second squares cancel second squared. 2 seconds, that would give me plus 28 feet, and plus 825 feet, whatever that comes out to be.
Huge number.
It's way up there, right? Yes, Jamie.
So a quick question about the homework. So you're saying that we could do problems out of the book? How do you
Instead.
know how many we have to do out of the book?
Same number.
Same number as what's on the book?
Yep, roughly. Yep. Okay?
And then you have to find when it hits the ground and what time it hits the ground and what's the velocity.
Okay, so when would the stone hit the ground?
What position it goes on.
And what's the speed when it hits the ground? Well, what do you know about when the rock hits the ground? It's always nice to have a picture.
Position is
0.
What's the position down here?
Negative 825.
So,
well, yeah, no, it's
depends on where you put your origin.
Yeah.
You're right. So if you put your origin here, it would be at negative 825.
isn't that what we did? Because that's a
So,
825 feet.
I didn't. I set it here because I used 825 feet, not 0 feet.
Right.
But you could. I mean, there's no reason not to. So in this case, when does S of t equal 0? That's when it hits the ground. Basically, use the quadratic formula to find it, right? And the quadratic formula will give you the time. And once you have the time, plug the time into the velocity function, and that will give you the velocity at which it hit the ground.
How important are the units going to be when we're doing these problems?
I always leave the units in. It's the physics background in me, but I know half of you are going to leave them off. And I'll try not to cringe.
Force it.
Can I ask one more question?
Yeah.
Why is the second squared, it goes down in the position?
Ask again.
It's second squared and then it's seconds and then it's just feet.
Oh, why does it go
Yeah.
down?
Yeah.
Because time squared carries the units of seconds squared.
Okay.
So those would cancel and give you feet.
So it's just the same.
Yeah, it's the same. Because t itself has units.
Oh.
And because t has seconds here, if I don't have a second in the denominator, they won't cancel to give me feet.
Okay.
And position should be feet plus feet plus feet.
Yeah, it wasn't.
Which is why I always leave the units on. Okay? Does that make sense? Does everybody feel a little bit better about homework out of 410? I did not. I'm kind of wondering if maybe somebody messed up and switched the homework for 410 and 5.5. Because what I saw from working with some students before class would have been better out of 5.5 and not out of 410.
In that case, actually switched 5.5 is going to be a breeze.
Yeah, by the time to get there. Okay, so we have 10 minutes left. What I want to do now is those of you who have not done the L'Hopital's quiz, do the L'Hopital's quiz now. The rest of you have already done L'Hopital's. You are free to go.